In this first item on our second test of spring 2017, clearly I used the same headers as a previous test, but totally different problems. We have a truss that has a whole series of vertical loads, probably representing gravity loads. And note that we have a cantilevered segment of the truss. Here's a support pin B and a support roller G. We're asked to find the member forces in these four members through this one particular panel or section of the truss. And that should be an indication right off the bat that there's something a little bit different going on here. Four forces, but we only really have three equations of equilibrium to work with as we were to cut through that particular one panel. So we've talked about this before, that when you have the situation of an X where two members overlay each other, there is no connection there. You have to start asking yourself, are those potentially tension counters? And that's got to be our basic assumption in this problem, is that CH and GH are tension counters. Unfortunately, don't have anything information about the size of the members that indicate that, but if they're not, then we would have a situation where we would have 1, 2, 3, 4 unknowns, 3 equations of equilibrium, and that would be a statically indeterminate problem. So in statics, we don't have but any choice in this case to either assume that there's a connection here, which would change the problem and make it feasible for us, or to assume that we've got tension counters. And so since we are told that they are overlaid, there is no joint there, and therefore we really have to assume that there are tension counters, right? And so that free body diagram that I drew real quickly really serves as our first step here. And let's draw that free body diagram in a slightly larger scale, where we haven't presumed which member is in compression and which member is in tension yet. Let's see if we can figure out what might be going on. There's our 2 point loads that have been imposed, and note that the panel here, shear, is going to have to clearly be going up. It's also going to be of magnitude 4.8 kips, and as such that would mean that that would drag this diagonal along with it, put it in tension, and it would take the other one and it would put it into compression. That would be GD, and the other one would be CH. And since GD is in compression and it is a tension counter, it buckles, and therefore GD would be a zero force member in this particular case. Not because of the equilibrium, but rather because being tension counter, that means it's long and skinny, and we're going to presume at this stage of our analyses that it buckles. And then we'll presume here that GH down at the bottom is in compression, and we'll presume or assume that CD at the top is in tension. The math here will demonstrate to us in just a moment that that is correct. And that math, of course, would be our equilibrium equations. If we sum forces in the Y, let's take upwards positive, we'll have the H component of the diagonal minus 2.4 minus 2.4 equal to 0, so therefore that Y component equals 4.8, that'd be the panel shear. And then note that the geometry of that triangle is such that it's 9.6 high, 11 side to side, and square root of the sum of the squares, that will turn out to be 14.6 on the horizontal. So note here, plus means that we guessed correctly the direction. That direction is tension, so we guessed all of that correct. CH equals then the whole magnitude, 14.6 over 9.6. That's the hypotenuse over the vertical. That's what component we had found, times 4.8, and that would be equal to 7.3 kips. Again, plus as shown, therefore tension as shown, and CH equals 7.3 kips. Right, so that's one of them. And we still got then the top chord, bottom chord ones to do, and in classic fashion we would do those by summing moments about some joints here. We've got, if we go down here to H, we'll get rid of CH and GH. Let's take counterclockwise as positive. We'll have CD times its moment arm, that's the height of the truss. And then the 2.4 goes through, DG is 0, CH goes through, GH goes through, so we just have then the 2.4 out at E, its moment arm is 11, set it equal to 0, and therefore CD will equal 2.75 kips, plus as shown is tension, so we end up with an answer of 2.75 kips of tension. And one more. And there we'll sum moments about point C, getting rid of then CDCH, DG again is 0, so we don't have to worry about that. We'll take counterclockwise as positive once again, and then we'd have that again, height of the trusses or moment arm, so 9.6 GH minus 2.4 times 11 minus 2.4 times 22, set it equal to 0 for equilibrium. Therefore GH will equal 8.25 kips, plus as shown, and as shown this time is compression, so therefore GH equals 8.25 kips compression. So summarize real quick here. The key is recognizing that we have tension counters here and here, and then following that up with, that means that one of those must buckle when they're in compression, basically having no resistance to any compressive force, and that's what enables to have a statically determinate problem where we can then execute these steps that you see down below.